Welcome back, everybody. So we are going to continue and finish this first lecture. It's very likely that we are going to end a bit early. All right, so this is the TA team with 6 wonderful TAs. So what are we going to be doing during this lecture? What is the menu that we are going to start with next week? First, we'll start something very simple that's called Boolean retrieval. Introduction was today, right? This is what I'm taking care of today. So we look into Boolean queries. It's a very primitive system. In fact, this is the very early systems, computer-based, work pretty much like that. So we'll see that the idea is that you look for specific keywords, but with Boolean formulas, like you want both the word information and retrieval in the same book, or maybe you want the word information or the word retrieval, so and or not, and the whole Boolean logic in there, right? So this is already a mini query language. Of course, it's not going to be SQL, but it's still going to be a query language. And so we look at the secrets of that. How do we make it work? How do we make it efficient? To access the data with Boolean queries. So these are the secrets that we are going to be unveiling next week. Then, still parts of the basics, we are going to be looking more into the details of the words that we are going to index. So what languages are made of. I think it's in that week. Yes, it's in this week that I'm also going to give you some quick 101 overview of languages. And I mean here not programming languages, but human languages, to make sure that you get a feeling for the diversity of human languages. You know, that there are features of English, or even in most of you, I think, anyway, speak already 2 languages. So, but there are many, many different features across the world. Some languages, for example, Arabic gets written right to left instead of left to right. There are languages where you have gigantic words. German is actually one of them because of the way you paste words together. But there are languages, as we will see, where the entire sentence is a single word. Then we look at all the interesting aspects of languages. And of course, the language that you want to index actually plays a role in the sort of structure that you are going to use, right? You wouldn't use the same technologies for English or for Spanish or for German because of these aspects of the language. What is a postings list? Well, this has to do with Boolean retrieval, but I just don't want to tell you just yet, but it's part of the structures that we are going to be building in order to make the system work. And in that week, based on the languages, I will also get a bit further into the discussion of postings lists. All right, so we are still here in the basics of information retrieval. Then, still in the basics, we are going to be covering tolerant retrieval. What is tolerant retrieval? Well, you probably noticed if you try to type something into a search engine that has a spelling mistake, you're going to get a "did you mean this and that" suggestion. Sometimes the engine will not even ask you for your opinion. They will just go ahead and query with the fixed mistake, right? You can still revert it. This is called tolerant retrieval. It's the idea that you account for the fact that the user is making a mistake and you're actually supporting the user into finding what they are looking for. But we need this technology in order to be able to say when we fix a mistake. How do we fix a mistake? How do we see that there is a spelling mistake? If there is a spelling mistake, how do we fix the spelling mistake? And again, we will see this also depends on the language a lot, in fact. All right. And then the second part of the semester, so here that will be the first 4 weeks, and then in week 5, so that's probably going to be end of March, beginning of April, we are going to start doing the advanced things, but still at the bachelor's level. The first advanced topic that we are going to cover is the scale-up. This is this big data I've been telling you about. Because this technology of the postings list and Boolean indexing and so on we're going to do it in a single laptop. Well, not the laptop, it's going to be a server hosted by the department, but still a single machine, right? So, but we will see that if you try to index the entire Library of Congress or the web, then a single machine is not enough. So how do we scale that up? We are going to borrow a few big data technologies that we do a bit ahead of time, that normally we're supposed to do it in big data lectures, but we are going to borrow a little bit of that, but just what we need in order to scale up the building the structures we need for information retrieval, right? So this is going to be a scale-up week, and that will include, in fact, MapReduce. Who heard of MapReduce? Right, so we will see a bit, it was a buzzword back then. I think maybe 10 years ago, the entire class would have the raised hands. But basically, we will use MapReduce as part of the solutions that we use in order to scale up. And of course, what are the challenges of scaling up? Well, this is exactly what I told you with capacity, throughput, and latency, is that we have gigantic amounts of data, but we cannot read them fast enough. So we have to find ways of parallelizing, right? By the way, somebody asked during the break, but maybe I can tell that to everybody. What I haven't told you, this is related to scale up, so this is why I'm doing this parenthesis now, is that capacity has increased, throughput has increased, but latency decreased. That's the opposite. You want a low latency, but you want high capacity and high throughput, right? So the latency decreased by 150. But what's the problem with throughput and latency? Why is it problematic that there is a batch? So I think here everybody understands why it's problematic. We just cannot read fast enough the data we have. Why is it problematic that we have now a mismatch here? Well, the idea is that when you download something, let me take the example of downloading something from the internet or even opening a web page. This is going to happen in two phases. In the first phase, you click, so you type the address, you click, and you probably noticed that for 1 or 2 seconds, the screen remains white, blank. There is nothing. This is the latency part. It's communicating with the server, but didn't get an answer yet. So 1 or 2 seconds, and then the things appear, and it's downloading. So there is the latency phase where you just wait without doing anything, and then there is the download phase where you actually ship over the data. Right? So imagine that, let's take as an example, it was taking 2 seconds for the latency part. That's very pessimistic. It's a bad system for 2 seconds because that's even more than the speed of light around the Earth, but let's say 2 seconds. And then imagine that it takes you 10 seconds then to download. This is then because of the throughput, because the bandwidth of your connection is limited. So it takes 10 seconds to download the whole file. So in total, 12 seconds. Now, this is the before. Now to the after, let's imagine that now these 10 seconds takes 10,000 times less. So if I'm correct, I'm doing it, that's right live in front of you. So 10 seconds divided by 10,000 is 1 millisecond, right? So technically you would download in just 1 millisecond instead of 10 seconds. Just parentheses, this is totally unrealistic, but I'm just for the purpose of computation. So these 10 seconds would become 1 millisecond with these improvements. Now, these 2 seconds, if I divide the 2 seconds by 150, I would probably get something like 14 milliseconds, right? Roughly 2000 divided by 150, probably something like 14. So what do I have in the after picture? I have 14 milliseconds of waiting time, and I have 1 millisecond of download time. Again, I repeat, before 2 seconds of latency, 10 seconds of downloading. So most of the time is spent downloading. But after, corrected by these 2 factors, I spend 40 milliseconds in latency and 1 millisecond downloading. So you see that the after picture is totally different. I'm actually spending most of the time waiting for things and very small amount of time actually downloading things. So you see that this discrepancy completely changes the way that it feels to actually download and ship data over the network, completely changes. So this is the reason why we use batch processing. Batch processing just means that instead of downloading a single file at a time, imagine, I'm pretty sure you've been through that. Imagine you want to upload 1,000 files to a server, FTP or whatever. you will have latency for each one of the 1,000 files. What do? You just put it in some tar file, right? And then you ship the tar file just once, right? How many times do you have latency? Just once for the tar file. And then the rest is just about shipping the tar file. This is called batch processing. When you just group together 1,000 little things into a single big thing, and then the waiting time will only happen once. This is batch processing. For whom does that make sense? Okay, this is such an important concept that I wanted to make sure it is clear. But again, we'll come back to that in the scale-up phase. In fact, this is something that we already feel today because maybe some of you have experienced a slower internet in your childhood, but back then when I was young, well, I'm still young, but I was younger. When you connected to the internet, most of the time was spending waiting for the page to load. You would enter an address, and then you would see the pictures of the page slowly appearing one by one, even almost pixel by pixel, just like this, and it would take 10 seconds to load the entire page, right? So this was throughput dominated. How does it feel today to use the internet? You click on the address, you wait for 1 or 2 seconds, and then the page displays instantly. That's pretty much how it feels. So the whole internet experience is totally different today than what it was 20 years ago, and this is because of this latency versus throughput thing. Okay, scale up, enough said about that. Then we'll have index construction, which is about how the techniques that you use. It's related to scale up, but the technique that you use to actually build an index also incrementally. What if you have updates coming in, on the fly? Because you have 2 ways of indexing things, right? If it's the Library of Congress, then you already have the 100 million books in there, and you just index the 100 million books. But the library and the web, they are alive, kind of, right? You have constantly new books incoming, new web pages that arrive. How do you update the index instead of rebuilding it from scratch every time, right? So there are techniques. This is called online indexing, and we'll also cover this sort of techniques and see how that there are tricks that are actually quite useful to make it efficient. Then we look into index compression. Index compression is the idea that whatever structures you build in order to have your information retrieval system, it's nice if you fit more into less space. Why? Well, for example, at some point, you basically reach the point that your laptop is not good enough. You have so much data that it doesn't fit anymore in your hard drive or in your memory. If you have compression techniques, it means that instead of buying a second laptop or going to the cloud, you can just compress what you have and continue using your laptop, but more efficiently, because you squeeze more into less space. So this is why index compression is useful. And in fact, it's a super interesting lecture because there's plenty of math in there on how do you compress sequences of integers. We'll see that it's all about compressing sequences of integers, and you fit more into less. And I think that trying to fit more into less space is, I would almost say, it's one of the core skills that I think you should be educated with as computer scientists. Because too many people make that mistake of thinking, okay, I'm just going to throw more money at it. I'm going to buy more machines. Many companies do that. It's too slow. Let's buy more machines. But in many cases, it's just better to just try to already use the hardware you already have and squeeze more out of it. And this is all about developing a feeling, not just a feeling, actually, also enthusiasm for getting more from the same hardware. And this is the sort of skills that are very useful. For example, if you work in big tech companies which maintains websites that are used by millions of people, then every single millisecond that you squeeze actually has a direct impact on the experience of the users and even the cost of the company. So the idea of trying to make more with less is really super interesting, and this is really something that the value that you can bring to your employer also based on that. So this is index compression. Then we are going to look into my favorite week, which is ranked retrieval, which is the idea that in the first weeks of the lecture, we are not going to rank anything. We're just returning results, but there is no order of the results, right? Either a result is part of the output or it's not part of the output so far. But in ranked retrieval, we start ranking things. In fact, if you use a search engine, things are ranked. You get a top 10, the top 10 results. Maybe some people will press next a few times, but that's it. Nobody will go 10 or 20 times, so it's very rare. So the ranking is actually very important, and it has the notion of score. You have to assign a score to every document, and then you sort by score and return the top score. And of course, one of the challenges here, and I leave that as an open thing, what if you have 100 million documents that your query outputs, and you need to sort them and output the top 10, but it only takes a few milliseconds? How do they do that, right? And we'll see how they do that when we target ranked retrieval. One of the reasons why I really like this week is that we are going to be using linear algebra. So you might have been wondering, why on earth am I doing linear algebra analysis in a computer science curriculum? Well, if you took machine learning, it should already be pretty clear why linear algebra is useful, but it's also going to be useful for ranked retrieval because we will see that the documents and the books literally are vectors in some vector space. And we are going to use the metric and the distance mechanisms in order to interpret the query. So this is going to be very abstract, but also super interesting, right? So this is ranked retrieval. And then we are going to start optimizing things a little bit. Again, trying to squeeze more from less and optimizing the scoring in order to output documents. We are going to see that we don't need to find exactly the top 10. In fact, it's enough to find the approximate top 10 because the user experience is actually not very different if it's only an approximation. And by approximating, you can actually be faster and more efficient. All right, this is scoring optimization. Then we'll have a week on evaluation. Evaluation is about having a way, formally, but also intuitively, to tell whether an information retrieval system is a good system or a bad system. You need also metrics for that allow you to say and evaluate the system. So we'll look into this. So this includes, for example, precision. I'm sure you heard of that. Precision, recall, sensitivity, and so on. So we'll cover all of these metrics and see how this is all done. You might have heard, even if it's not precision and recall, maybe who heard already of type 1 errors and type 2 errors, at least in the context of machine learning? Some of you, oh, maybe you, who already took the machine learning class? Who is taking it right now? Okay, so you will hear about type 1 errors and type 2 errors. I have to be honest with you, I never remember what is 1 and 2 between precision and recall, but there is a correspondence between type 1 and type 2 on false positives and false negatives. All right, so this is the evaluation of the system. And actually, you will see a lot of similarity with the machine learning evaluation techniques. And in particular, I can already tell you right now, accuracy is not the way to go. That's not a good evaluation matrix. Just like the bubble sort of evaluation would be accuracy. Okay, and then at the end of the semester, we are done now at that point with the bachelor's level. So this is always typically taught at the bachelor's level, pretty standard in universities. And then we'll start with master's level things. I'm pretty sure you won't be scared of that. It's also pretty exciting. The first thing that we will do that is more advanced is a totally different approach to information retrieval that is not based on anything we've seen before. It's all based on probabilities and the Bayesian formula. Right, probability of A knowing B equals to probability of B knowing A times the probability of A divided by the probability of B. Who already knows that one? Bayesian formula. So we'll see how we can put it into practice. And just like a rabbit out of the hat, we get an actually working information retrieval system, which is actually pretty impressive. All right, so only based on probabilities. Okay. And actually, this is actually more current than ever, even though it's already been in the book for a pretty long time, but somehow now there is a revival of these things. we look into language models. So the language models are another series of techniques to do information retrieval. It is related to generative AI, but indirectly. The use of language models in information retrieval is not about building some ChatGPT. It's really about building an information retrieval system where you enter keywords and get some things. But it turns out that the tools that you use that are based on Markov chains and the like, the idea that when you have a series of 10 words, what is the 11th one, and so on. This is similar to the sort of things you do in ChatGPT. So this is why when you use ChatGPT, it actually puts it one word at a time. If you slow it down, you really see word by word. But this is actually based on language models. So of course, the language models we're going to see are not going to be as complex as ChatGPT, but it's still going to be quite related. And we'll see that based on these language models, we can also, once again, come up with a totally new way of doing information retrieval that's not the same as probabilistic. It's again another one based on language models. All right, and here we'll see actually a few, you probably saw it, covered it already, right? The deterministic automata with all these fancy circles that light up when you consume letters of words, right? So we'll actually see that in the language models too, in the context of regular expressions. I don't see your faces light up. Have you covered that? The deterministic automata, regular expressions? Yes, awesome. So we'll see them in the language models, but we're going to do something funny. And in fact, this is the good thing about generative AI. We are going to use the model that is actually the deterministic automaton, but we are just going to revert the input and the output. This is how you get into generative mode, right? Instead of consuming a word, you produce a word. You just turn it upside down. So this is what we'll be doing with this deterministic automata. And then, if time permits, I might say a few words about crawling the web and link analysis. That would be PageRank, for example, the algorithm used by Google to index the web. So we'll see if time permits, right? So these are the alternate methodologies. Okay, so this is the menu. So I hope that I could get you a bit excited about that, and that will keep us busy during the entire semester. So what is expected? So there is this weekly lecture. It's going to be every Friday from 10 to 12, 2 hours. Then we have the exercise session, right? This is every Friday, 4 to 5. I think they are all at the same time, if my memory is correct. And there's one exercise slot per TA. So you should register for the groups if you haven't done so already. If you run out of slots, then tell us. We will see how we can arrange. Yes, so what's important is there is no exercise session this week, right? There is nothing. So today you shouldn't go anywhere. It's next week that we really start with the serious things. So right now the TA team is preparing the Jupyter Hub that is hosted by the department. So we will use to give you the exercise notebooks. They will be uploaded to the Jupyter Hub. Then you will just be able to connect with your ETH credentials. And this is being set up right now, and it might be that before next week, you'll already get news from the TA team who ask you to please connect and try it out and check that it works. And you'll also get some Python tutorial as well, just to make sure that those who do not know Python, they have an opportunity to catch up. But you'll see it's really no big deal. We are not going to use advanced features of Python, but it's going to be quite useful for you to implement a few things, right? So some of the exercises will be theoretical. So we'll ask you, questions and grade it. And some of the exercises will be based on programming. We'll ask you to actually program something or implement some aspects of what we're covering in the lecture. We carefully picked the topics, meaning that in order to avoid distraction, every week there is only one specific thing to implement, right? You won't have to implement everything, but we pick one aspect and ask you to try to implement it in the Jupyter notebook, right? So this is what we use Jupyter Hub for. Then there is the reading material, but actually it's pretty easy because we are using the book by the Stanford NLP people, so called Information Retrieval, and almost every week there is a chapter. So at first it's easy because every chapter corresponds to a week, but then after a while it's no longer the case. So I will tell you exactly what to read exactly when, right? But at the beginning, it's really almost a mapping of 1 chapter equals a week. So please read the book. I should not even have put an S here. There's only 1 book really, but really make sure that you read it. It's complementary to this lecture. All right. And then at the end, there is the written exam that's going to take place in the summer session, and for 3 hours. We give you a lot of time so that you can really think about each question. So more time that you normally need. Our goal is that it's doable in 2 hours, but with 1 more hour, that should relieve a bit of pressure on you. So it's a general recommendation at ETH that the exams are not taken under pressure, but you really can take the time to think about your answers. Okay. It's going to be somewhere between August 7th and September 1. We just don't know the date. You know, this is just as usual every semester, but probably in May or end of May, we're going to know the date. It's not possible to take preponed or remote exams. This is a computer exams in a computer room, either in Earlycon or in the main building, Moodle-based, similar to some of the quizzes you're going to get during the semester. And without any programming environment. I think this is just going to be just Moodle. But if it changes, we'll let you know. Okay. And if all of that is, well, technically not all of that, you just need to pass the exam to get the 4 credits. But of course, in order to pass the exam, it's a good idea to consider the dependencies of that, right? Now, good news, we have bonus points. That was introduced a couple of years ago and harmonized at ETH. So you have an opportunity to get an extra quarter point for your exam. I'm going to tell you how you can get an extra quarter points for the exam. 3 of the weeks of the semester, you're going to have a graded quiz. If you pass the graded quiz twice, meaning in 2 of the 3 weeks, if you pass it twice, then you get the full quarter point. Right? So it means that if you pass the first 2, then you're good. You have the bonus points. If you miss 1 of the 2, then the 3rd week is an opportunity to catch up and still try to get the bonus point, right? So it's all or nothing. Either you get 2, you pass 2 of the weeks and get the quarter points, or you don't, right? Then it's added to the exam grade, except if you have a 6, which of course I wish to you, but if you have a 6, you're not going to get a 625, right? It's still going to be a 6. Okay, but I think if you have a 6, you're going to be so happy anyway. That's okay. So this is the book Information Retrieval that we are going to use. I think it's available online on nlp.stanford.edu. So it's there, but you will also find it in the ETH library. I think it's also right here in this building in the Informatic Bibliothèque. So it's a good idea to go there and find it. And again, I recommend reading it. It might be that on the NLP website of the Stanford team, you might have some solutions of the exercises in the book, which can also be quite useful. All right, so we're going to use Python. I know that some of you already know it since I asked you a bit earlier. I already did the question. So we are going to use the Jupyter notebooks as part of Jupyter Hub, hosted again in the department. So we care about data protection, so we really made a conscious effort to not have anything in the cloud or using cloud services, but to really host everything at ETH, right? So the Jupyter notebooks are hosted right here on the department's computers. So the exercise session again starts next week, 4 to 5. So you just need to go to the room where your group is. If there is demand for having 1 session hybrid, let us know. Then we'll see if some of the TAs agree to do it hybrid, or at least one of the TAs. We'll see. For the recordings, I cannot guarantee anything. This is really at the discretion of the TAs. But in any case, what we will not do is put any recording publicly, right? For the lecture, yes, this is all on YouTube. But for the exercises, we do not put them publicly. This is just, it would be just on the Moodle internally, just for the purpose of the course, because we want you to be comfortable, right? Okay. So please make sure, if you haven't done so already, to register in My Studies, because this is how you get access to the course Moodle and automatically, and to the material of the lecture. So make sure that you do that. Okay. Oh, this I forgot to fix that. There's actually, is it 5? We have 5 sessions, right? And this is if we'll see if we have demand for that, if we can implement something like that. Okay. Next, we have a chat server at element.int.ethg.ch. Again, it's hosted at the department. It's not Piazza or anything. This is right here at ETH. So please, everybody, connect to it once with your ETH login and password, because we can only add you to the chat room if you have logged in once. Otherwise, we cannot find you. So we probably do it once a week. We again do a full scan to see if new people have registered. But if you could all do it now already, or when you're watching us on YouTube, do it now. Log in. Just takes you a few seconds, and then you're in there. And then we'll do a general invitation for everybody. I don't know if you'll get a notification. You just need to try again a few days later, and you should have access to the course space. If at a later point you still don't have access, or you registered later, then just drop us an email and we'll make sure to give you access. The Moodle is right here, but normally it should be linked from the course catalog, but this is the address, and this is where all the material will be, the slides, the pointers to the recordings. Even for the recordings, you can also just go to the YouTube channel, and you know, it's always if you want to have them as soon as they are released, then it's best to directly look at the YouTube channel. But then at some point we also add the links to the Moodle repository, and the exercises will be there as well. The Jupyter notebooks, I think they are directly uploaded to the Jupyter Hub, so probably we'll duplicate them also in Moodle, but they will be uploaded to the Jupyter Hub where you will find them. I'm clicking and nothing happens. And I think it's good because we are at the last slide. So it's great because now it's 47. So you get to go to the Mensa early and not even have any queue, which I hope you will appreciate. So thank you very much for coming today. I hope to see you next week, and we'll start looking into Boolean queries. Again, no exercise session today. It starts next week. Thank you, everybody. Have a great day.